Hello everyone, this one is Mr. Terrefa. Now we are on the second chapters of chemistry of natural products. In the first chapter, I'm sure that you are interested with the video tutorial I prepared for you, and this is the next part, which is chapter 2 is all about stereochemistry. It is the science behind the three-dimensional nature of the compounds. Yes, so under this stereochemistry, we try to cover what is stereochemistry and what is stereoisomers, and how this stereochemistry can have effects or influences on the drug discovery scenario from natural products. So the two major classes of isomers, to remind you that, recall that isomer are different compound with the same molecular formula but different structure. It means you know that this one is isomer. So isomer is any molecule that are different compounds with the same molecular formula but different structure. It means so the two major classes of isomer are either constitutional isomers or stereoisomers. It means there are two major classes of isomer. Isomers are constitutional isomer and the stereoisomers. These constitutional or structural isomer have different IUPAC name and the same or different functional groups and a different physical property as well as different chemical properties. So any compound that have different IUPAC names, different chemical and physical property as well as functional group can maybe act as constitutional or structural isomers. When it comes to stereoisomers differ only in the way the atoms are oriented in space. They have identical IUPAC names except for the prefix like cis trans. They always have the same functional groups at me. So the particular three-dimensional arrangement is called configuration, and these stereoisomers differ in configuration only. So the comparison of constitutional isomers and the stereoisomer can be depicted as follows. For example, if you take 2-methylpentane and 3-methylpentane, they are similar molecular formula and similar structure, and only the position of methyl group can be differ from the case of 2-methylpentane on the second carbon and 3-methylpentane on the third carbon. Therefore, such type of isomer is known as constitutional isomers or structural isomer. That means having the same molecular formula but different names. And when you come to stereoisomers, these stereoisomers can be what the three-dimensional structure of the compound can be differ. For example, cis 1,2-dimethyl cyclopentane is quite different from trans 1,2-dimethyl cyclopentane because the position of CH3 or methyl group is both two methyl group can be worked toward the viewer, and when you see in the trans case, one methyl is away from the viewer and one is toward the viewer. Therefore, this show that stereoisomers can be depicted like these structures. So have a look. This example are the following pair of compound, constitutional isomer or stereoisomer. The question is that to identify whether the given compound A, compound B, and the compound C can be either structural or constitutional isomer. Have a look at in case of A, this compound can be differ only in the position of methyl group. Therefore, if something can be differ on only the position of one methyl group and having the same molecular formula, such compound is known as constitutional isomer. So A is constitutional isomers. Yes, constitutional isomers. Whereas in case of B, it shows us the position of two methyl group on the same carbon and on different carbon. Therefore, such type of compound is also at constitutional isomer or structural isomer. but in case of C, this shows that the 2-methyl group attached on cyclobutane can be what differ in the 2-methyl group can be toward the viewer, and in the other case it is away, one is away from the viewer, which means that cis and the trans isomer are there. This one is exactly stereoisomers. So in this stereoisomer, you have to know the concept of chiral and the achiral molecules. Also, everything has a mirror image, and this mirror image may or may not be superimposable. So stereoisomer is what? A mirror image, but this mirror image may not be superimposable. So some molecules are like hands, because we have left and right hands. These two left and the right hand is a mirror image, but they are not identical, which means that they are or superimposable, that it means. So molecule or object that is not superimposable but they have a mirror image is said to be what? Said to be what? Stereoisomer. Stereoisomers. Or this such stereoisomer is what? Chiral compound. Says that chiral compound. Or if stereogenic carbon having what? The 4 different substituents, we say that chiral. And if at least 2 substituents that attached on the stereogenic carbon or the carbon at the center is known as achiral compounds. So other molecules are like SOX. 2 SOX from the pair are a mirror image that are superimposable. A SOX and they are what? Mirror image, and that mirror image is identical actually, and therefore if 2 are identical we say that they are achiral rather than chiral. So a molecular object that is superimposable on this mirror image is said to be achiral, and a molecular object that is not superimposable on this mirror image is said to be chiral. SOX are achiral, they are a mirror image, that mirror image is superposable. This mirror image means that there is a plane polarized light, or there is imaginary lines that pass through the compound that shows what? Superposability, that is known as achiral. So we can now consider several molecules to determine whether or not they are chiral. Have a look water. Water is achiral because oxygen at the center can be surrounded by 2 hydrogen in the vent or V shapes. Due to this, 2 hydrogen are similar attached on oxygen. So if a compound having what? 2 substituents, at least 2 substituents are similar, is said to be achiral. But in the same fashion, if you look at the bonds on the chlorobromomethane also have what? 2 chlorine dichloro bromomethane have 2 chloride 3 chloride molecule or a chloride molecules, and 2 hydrogen molecule are what? Similar. Therefore such type of compound is also what? Achiral. A molecule labeled A and its mirror image labeled B are not superimposable. No matter how you rotate A and B, all the atoms are never aligned. Thus, CHBr-CLF is chiral molecule, and the A and the B are different compound. So A and the B are stereoisomers, especially they are enantiomers. A carbon atom with 4 different groups is said to be stereogenic center or tetrahedral carbons. This tetrahedral carbon is known as chiral molecule because the 4 substituents that attached on the stereogenic carbon is what? Different. So such type of compound which have a mirror image and a non-superimposable is known as enantiomers. It's known as enantiomers. In general, a molecule with no stereogenic center will not be chiral. There are also an exception also. With 1 stereogenic center, the molecule will always be chiral. With 2 or more stereogenic center, the molecule may or may not be chiral because of the existence of what Meso compound also there. So a chiral molecule usually contain a plane of symmetry, but chiral molecule do not. Plane of symmetry is a mirror plane that cuts the molecule in half so that one half of the molecule is a reflection of the other half. So such plane is known as plane of symmetry. Plane of symmetry. Plane of symmetry. So this plane of symmetry that pass through chlorobromomethane have a plane of symmetry, but in case of chloro, bromo, fluoro, methane have no plane of symmetry. Therefore, if something lacks plane of symmetry, we say that chiral. If something have a plane of symmetry, we say that achiral. So such criteria also are a distinctive feature for saying chiral and achiral compounds. Symmetry of the basic principle of chirality. So everything has a mirror image. The fundamental question is whether the molecule and its mirror image are superimposable. If the molecule and its mirror image are not superimposable, the molecule and its mirror image are said to be chiral, and as the term stereogenic center and the chiral molecule are related but distinct. In general, a chiral molecules must have one or more stereogenic center. The presence of plane of symmetry makes a molecule chiral. Therefore, the distinctive feature between chiral and achiral is one, the existence of plane of symmetry, which means if a compound have a plane of symmetry, we say that achiral, but if a compound have no plane of symmetry, we say that chiral. So chiral compound may have what, one stereogenic center or more than one stereogenic centers. So classify each of the following pair as chiral or achiral. So have a look at. So the stereogenic carbon that attached, that a center is surrounded by 2 methyl. Since 2 methyl group are similar, we say that achiral. Compound 1 is what? Achiral. But in case of B, but the 4 substituent, chlorine, bromine, hydrogen, and methyl group are different. Therefore, we say that chiral compound. And in case of D, since yes, we have this hydrogen, bromine, and fluorine. This carbon is one stereogenic center. Therefore, but here when you come to here we have 2 hydrogen. Therefore, this compound having the 4 stereogenic center is known as chiral. So stereogenic centers. To locate the stereogenic center, examine each tetrahedral carbon atom in the molecule and look at the 4 groups, not 4 atoms bonded to it. So always omit from consideration all carbon atoms that cannot be tetrahedral stereogenic center. Also, the principal criteria for identifying the existence of stereogenic center is what, looking the tetrahedral carbon rather than the remaining carbon. Therefore, carbon substituent afuriin marfamte ilaaluun dirqamata jechuudha. በአራት ካርበን ሴንትራል ካርበን ወይም ደግሞ በአራት ሰብስቲቲዩንቱ የተያዘችውን ካርበን ነው አይተን ስቴሮጀኒክ ሴንተርን መለየት የምንችለው ለማለት ተፈልጎ ነው። ሶ by this principle you have to identify what stereogenic center. So larger organic molecule can have 2 or more 3 or even 100 of stereogenic centers. For example, if you take propoxyphene with a trade name known as Darvon, which is analgesic drug have what, different stereogenic center. This arrow or this is show that this compound have what, stereogenic centers. This ephedrine also have what, 2 stereogenic centers, which is a bronchodilator or decongestant drug. This is simple sugar, fructose sugar. This sugar also have what 3 stereogenic center. This star shows that the presence of stereogenic center. So label the stereogenic centers in each of the molecule and decide if it is chiral. So have a look this compound. This carbon have no stereogenic center. This also have no stereogenic center. But this carbon, when you look this carbon, it have these 2 group which is similar. Therefore, it have no stereogenic center in general. Yes. Therefore, the compound is what? Achiral. The compound is what? Achiral, because these two substituent is almost similar. When you look this one, you look this stereogenic center, it have what? Chiral compound. Yes, because of stereogenic center are there. When you look this one, this carbon also have what? Different one stereogenic center. Therefore, the compound is what? Chirals. Have a look this also. How many stereogenic center are there? Yes, you have to guess at least This is one stereogenic center, this also another stereogenic center. Therefore it have two stereogenic center. It have 4 enantiomer, it means, because number of enantiomer is equal to the power of n, where n is stereogenic center. This also have second, again this one is also third stereogenic center, therefore to the power of 3, which means that 8 enantiomers are there for this compound. When you look this one is having one stereogenic center, this also another stereogenic center, and therefore it have 2 stereogenic center, means to the power of 2 having what, 4 enantiomer, it means. So to draw both enantiomer of chiral compound such as 2-butanol, use the typical convention for depicting a tetrahedron. So you have to observe what, tetrahedral carbon. The carbon having 4 different substituents, that means place 2 bonds in the plane, one in front of the plane on the wedge and one behind the plane on the dash. Then to form the first enantiomer, arbitrarily place the 4 groups hydrogen, OH, CH3, CH2, CH3 on any bonds to the stereogenic center. Then you have to draw the mirror image. Then by this principle you have to identify stereogenic center and the number of enantiomers. Also you have to identify by this principle. So this one is an amino acid leucine, which have one stereogenic center also, and the bromohexane also have one stereogenic centers. So the carbon having what, 4 different substituents, therefore to the power of 1, at least it have what, 2 enantiomers. Locate each stereogenic center and draw both enantiomers. So these have almost only one stereogenic center, therefore this stereogenic center have its own mirror image. So this 2 mirror image shows that the existence of enantiomers. These will also have its own enantiomers. So stereogenic center may also occur at carbon atoms that are a part of the ring. So to find the stereogenic center on the ring carbon, always draw the ring as a flat polygon and look for tetrahedral carbon that bonded to the 4 different groups. For example, this one is stereogenic centers. How? Because this one is one group, this one is another group, and this group is also another group, but this and this is not symmetric, are not similar, therefore it is different group. Therefore C3 is what, stereogenic center for C1 is stereogenic center for this one, and in case of this compound, C1 is not stereogenic center. Yes, because 2 identical group, yeah, this one is what, symmetry, and again this one also symmetry, therefore 2 identical group can be surrounded this carbon or the carbon, therefore there is no stereogenic center. In case of here, but these 2 group is what, different because of double bond here, and this is a top group and this is a bottom group is quite different, therefore at this position there is stereogenic center. So in 3-methyl cyclohexane, the CH3 and H substituent that are above and below the plane of the ring are drawn with wedge and dash as usual. Yeah, this one is having got 1, 2, 3 stereogenic center are there, therefore to the power of 3 it is 8 enantiomers are there, that means. So labeling stereogenic center with R or S, since enantiomer are two different compounds, they need to be distinguished by name. This is done by adding the prefix R or S. R is for rectus and S is for sincere, which is to the left, and R is to the right, it means to the opaque name of the enantiomer. Naming enantiomer with the prefix R or S is called Can in gold prolonged system. This one is the name of scientists for the first time, the one that try to label and put this rule for the for identification of enantiomers. So designate enantiomers as R or S. The priority must be assigned to each group bonded to the stereogenic center in order to decreasing atomic number. So the 4 substituents that can be attached to the stereogenic center can be given the number according to their atomic number. The highest atomic number gets the first priority, and the least atomic number always or almost usually hydrogen can get what, the 4th priority. Therefore, by simply using the rotation from 1 to 2, 2 to 3, 3 to 4, you have to identify whether it is R rectus or S or syncytial. If two atoms on stereogenic center are the same, assign priority based on the atomic number of the atom bound to this atom. And one atom of the higher atomic number determine the higher priority. For example, if you look this one, oxygen gets the highest priority because of the atomic number of oxygen is greater than that of carbon, and carbon gets the second priority than the hydrogen. But here is carbon, here is also carbon, so you have to compare this carbon with this carbon. They are similar, but this hydrogen with this hydrogen, two hydrogen with two hydrogen, one remaining hydrogen can be compared with this carbon. Therefore, since this carbon is greater than the hydrogen, this gets second priority, and this gets third priority, this gets the first priority. So this one is 1, this one is 2, this one is 3, this one is 4. Therefore, the rotation is seems like this, but you have to first exchange the two groups so as to rotate the plane polarized light toward this direction, which is known as S or syncytial. So if two isotopes are bound to the stereogenic center, assign priority in order of decreasing mass number. Thus, in comparing the three isotopes of hydrogen, the order of priority like this. For example, tritium, you know, the 3, and deuterium is 2, and hydrogen is what, 1. So the priority is always given like 1. For this one is 2, this one is what, 3, because of the atomic mass number of tritium is by far greater than that of hydrogen. To assign the priority to an atom that is a part of the multiple bond, treats the multiple bonded atom as an equivalent number of singly bonded atoms. For example, carbon of carbonyl is considered to be bonded as 2 oxygen atoms. That means, yeah, a single carbon can be attached with 2 oxygen bond, and you have to identify by this principle. So other common multiple bond are drawn like this one. For example, carbon double bond mean that one carbon with this carbon, the other carbon with this carbon, and the carbon triple bond mean that one carbon with this two carbon, and this carbon again with two carbon. So each atom in the double bond is drawn twice, and each atom in the triple bond drawn in 3 times that. So based on this, we have to assign. Now we have different example here. For example, chlorine, bromine, CH, iodine, and hydrogen are there. So the priority can be given for bromine for the first, because bromine greater than carbon and chlorine, the hydrogen as well. We didn't compare with iodine like this because it is far apart from. So this one is the first, this one is the second, but this one is the third, and this one is the fourth. There's a 4. Therefore 1, 2, 3, 4. But first you have to it's not bonded directly to the stereogenic center, the iodine, that it means. Therefore it cannot be compared with bromine, the chlorine, that it means. Therefore at least you have to exchange these two groups, and then you have to rotate like this, which is directly R or rectus. So by this principle, you have to identify different compounds, and you have to assign the priority based on their atomic number, as I mentioned before, and different examples are depicted here. You have to see the steps you have to follow. So if the rotation, I will look this. If the rotation is 1, 2, 2, 2, 2, 3 like this, we say that clockwise rotations or are isomers. But if it is counterclockwise like this, we say that is known as counterclockwise or S. This R and S is simply what a Latin term, syncytial and rectum mean. So which group in each pair has the highest priority? This or this? When you compare these two, this one is the first priority, and if you compare iodine with bromine, iodine is the first priority, and if you see this and this one is the first priority, because one carbon is equivalent with the carbon, two hydrogen is equivalent with this hydrogen, the third hydrogen can be compared with this carbon. Therefore this gate is the first priority rather than this. So yeah, you have to look this one. Yes, but I'm sure that here is some yeah, two hydrogen with one carbon with this carbon, and the two hydrogen can be compared with two hydrogen. The third hydrogen can be compared with carbon, but this bromine is directly bonded with this hydrogen, therefore this bromine is by far greater than this carbon, therefore this group can get first priority. The same is true for this. You have to arrange in decreasing rank in order of decreasing priority group, it says. So yeah, the first priority, second priority, third and the fourth priority is given for this. If it is double, triple bond, can get the first priority, in the second, the third is what like this. You are so you have to identify like this one. The other one is diastereomers. For a molecule with n stereogenic centers, the maximum number of stereoisomers are to the power of n. Let's consider a stepwise procedure for finding all possible stereoisomers of 2,3 cyclo dibromopentane. So first you have to draw the structure. Yes, draw one stereoisomers by arbitrarily arranging substitution around stereogenic center, and draw the mirror image of that compound. And then after you have to identify what's the stereogenic center. So if you have drawn the compound and its mirror image in the described manner, you have only to do two operation to see if the atoms align. Place B directly on the top of A and rotate B 180 degree and place it on the top of A to see if the atom is aligned. Therefore, you have to rotate in 180 degrees, and you have to see the difference between A and the B. So hydrogen and the B bromine do not align with each other. Therefore this hydrogen is away from the viewer, but this one is toward the viewer. So in this case, the atom of A and the B do not align, making A and the B are non-superimposable mirror image. If something is non-superimposable mirror image, we say that enantiomers, thus A and the B are the two of the four possible stereoisomers, because if we have two stereogenic center, we say that to the power of n or to the power of 2 enantiomers are there. Switching the position of hydrogen and the bromine or any two groups on one stereogenic center of either A or B forms a new stereogenic, which is labeled like C, and this example, which is different from A and the B, and the mirror image of C is labeled as DC, and the D are C and the D are said to be what? Enantiomer, because the two compounds are a mirror image but non-superimposable mirror image. Stereoisomers are not mirror image. Stereoisomers that are not mirror image of one another are said to be what? Diastereomers. For example, in the A and the C are what? A and the C are said to be what? Diastereomers, because they are not mirror image, they are non-superimposable as well. If something is not mirror image with each other, we say that diastereomers. Diasterome is difference. So here is different that example, which is a pair of enantiomer A and the B and the C and the D, and a pair of diastereomer AC and A and the D, or B and the C or B and the D are what? Enantiomer, because they are completely different different mirror image, non-mirror image, or they cannot be what? Mirror image together. Label the stereogenic center and draw all stereoisomers. This one is one stereogenic center, therefore we have what? To the power of 2, that is 4 enantiomer. It means this enantiomer is a mirror image of each other, but that mirror image is what? Non-superimposable. So the 4 enantiomer is labeled like this. These are enantiomers but non-superimposable. Let's see a meso compound. So meso compound is a compound that have a mirror image which is superimposable. So mirror image which is superimposable is known as meso compound. Let us now consider the stereoisomer of 2,3-dibromobutane. Since this molecule has 2 stereogenic centers, the maximum number of stereoisomers is what? 4. But here two compounds are similar or identical or mirror image of each other, which is superimposable. Therefore, to the power of n minus 1 is the number of meso compound. That means, because to find all isomers of 2,3-dibromobutane, arbitrarily add hydrogen bromine, the CH3 group to the stereogenic center, and forming one enantiomer A, and then draw its mirror image. That means, to find the other stereogenic center, if they exist, switch the position of two group, one stereogenic center of the one enantiomer only. In this case, switching the position of hydrogen, the bromine on one stereogenic center of A forms C, which is different from both A and B. Therefore, a meso compound is a chiral compound that contains tetrahedral stereogenic center, and therefore this C is known as a meso compound. This C is what? Meso compound. So a compound that have a mirror image, and the mirror image is what? Identical. This compound are a mirror image. They are identical. It means, therefore we say that meso compound. So compound C contain a plane of symmetry that is achiral. So a meso compound generally contain a plane of symmetry so that they possess two identical halves. Therefore, what makes the similarity between achiral compound and a meso compound are that a chiral compound by itself is known as meso compound, and this meso compound have a plane of symmetry, but a chiral compound have no plane of symmetry, as we mentioned before, because one stereoisomer of 2,3 dibromobutane is superimposable on this mirror image. There are only 3 stereoisomer, not 4 rather than cos to the power of n minus 1. Yeah, these two compounds are simply enantiomers because of their mirror image. These are also a mirror image of each other, but this and this and this and this are what's not mirror image, therefore they are diasteromers. They are superimposably mirror image or the same compound. These two are, therefore they are meso compound. Yeah, these are a meso compound due to the presence of what? Plane of symmetry. So R&S assignment in a compound with 2 or more stereogenic centers. When a compound has more than one stereogenic center, R&S configuration must be assigned to each atom. For example, this one is stereogenic center, this also another stereogenic center. Therefore, you have to give R or S configuration for this stereogenic center or stereogenic carbon, and the same is true for this one. During that time, this one is substituent, this one is another substituent, this one is substituent, and these all carbon can be considered as a substituent. When you consider this and these are plus these all compound can be act as a substituent. So based on their rotation, we say that either or R or S. So identical compounds have the same R and S designation at every tetrahedral stereogenic center. So enantiomer have exactly opposite R and S designation. The diastereomer have the same R and S designation for at least one stereogenic centers, and the opposite for at least one of the other stereogenic centers. It says that. So disubstituted cycloalkene are there. This disubstituted cycloalkene have 2 stereogenic center at this position. So consider 1,3-dibromocyclopentene. Since it has 2 stereogenic center, it has maximum of 4 stereoisomers. Recall that the disubstituted cycloalkene can have 2 substituents on the same side of the ring, cis isomer A, or on opposite side of the ring, trans isomer B. Thus, the compound are stereoisomer but not mirror image. Therefore, if 2 compound are stereoisomer but not mirror image, we say that diasteromers. Rather than enantiomer, we say that diasteromers. To find the other 2 stereoisomers, if they exist, draw the mirror image of each compound and determine whether the compound and its mirror image are superimposable or not. So these 2 compounds have identical because of cis position at that. Therefore, they are superimposable in this mirror image and making what? Identical or meso compound. Thus, this A is what? A meso compound. So the same is true for trans isomer is not superimposable on its mirror image, and the label C making C, B and C different compound. Therefore, B and C are enantiomers because one stereoisomer of 1,3-dibromocyclopentane is superimposable on its mirror image, and there are only 3 stereoisomers, not 4 again, because to the power of n minus 1. So isomer can be different compound with the same formula, and this isomer can be summarized like that. Isomer can be classified as constitutional isomers and the stereoisomers, and the constitutional isomers mean having atom bonded to different atom bonded to different atoms, but stereoisomer have atoms or isomer with different 3D or 3-dimensional arrangement. This stereoisomer can be classified also into enantiomers and the diastero. In case of enantiomers, having a mirror image which is non-superimposable, but in case of diasteromers, it is non-mirror image or not mirror images. So two non-identical molecules, do you have the same molecular formula? Maybe yes or no. If it is no, they are not isomers. If it is yes, it is isomer. So are the molecule named as the same except for the prefix such as cis, trans, R or S? If it is yes, that is stereoisomers. If it is no, it is constitutional isomer. The same is true. Are the molecular mirror image of each other? If it is yes, the compound is enantiomers. Otherwise, it is diasteromers. It is what? Diasteromers. So without looking at the structure, label each pair as enantiomer or diasteromers. So this one is one changes, one stays the same, so they are diasteromers. And in this case, both change can be what enantiomers, and these two changes, one stays the same or diasteromers. So diasteromers. So which one is meso compound? So this one is not meso because no plane of symmetry are there, but this one is a meso compound because of plane of symmetry are there. The same is true here, not meso because of no plane of symmetry are there, because different functional group are there on this compound. So draw all possible stereoisomer, then pair up enantiomer and the diasteromers, so giving the mirror image and to produce what enantiomers, and the opposite is true for diasteromers. So this A and the B as well as C and the D are exactly enantiomers, but if you compare, A is diasteromer for C and the D, and the B is also a diasteromers for either C or what. So state how each pair are related: enantiomers, diasteromers, constitutional isomers, or identical. So when you look, A is the same formula but the same as the configuration, therefore it is identical compound. But when you see B, same formula, cis and the trans, therefore if something is have cis and the trans, we say that diasteromers. When you come to the C, the same formula but opposite R and S configuration, therefore it is what? Simply enantiomers. Simply what? Enantiomers. So how we can identify the physical property of stereoisomers? There is optical activity, so the chemical and the physical properties of the two enantiomers are identical except in their interaction with chiral substance. They have identical physical properties except for how they interact with the plane of polarized light. Plane polarized light is a light that has electric vector that oscillates in a single plane, and the plane polarized light arise from passing ordinary light through the polarizer. There is a device known as polarimeter, is an instrument that allows polarized light to travel through the sample tube containing an organic compound. It permits the measurement of the degree to which an organic compound rotates plane polarized light. This plane polarized light can be rotated either toward the light or towards the left, or clockwise or anti-clockwise. By this principle, they produce either levorotatory or dextro rotatory. So with a chiral compound, the lights that exist the sample tube remaining unchanged. A compound that does not change the plane polarized light is said to be optically inactive. Therefore, every polarimeter of such arrangement, always there is a source of light or source of radiation are there. This is actually sodium D light, and there is ordinary light, and the polarizer are there, and this polarizer can be what? A sample tube. The sample holding tube are there, and this one is what a plane polarized light, a place where exiting a plane polarized light. So with a chiral compound, the same plane of polarized light is rotated through an angle alpha. That angle alpha is measured in degrees, and it is said to be what? Observed rotation. So a compound that rotates polarized light is said to be optically active, or chiral compound. So the rotation of polarized light can be clockwise or anti-clockwise. If the rotation is clockwise, meaning to the right of the noon position, the compound is said to be dextrorotatory, or D, or plus. If the rotation is counterclockwise, to the left of the noon, the compound is said to be levorotatory, or L, or minus I. So two enantiomers rotate the plane polarized light to an unequal extent but in opposite direction. Thus, if enantiomer A rotate polarized light plus 5 degree, the same concentration of enantiomer B rotates it to minus side. So this minus is L and this plus shows what D. No relationship exists between A and R and S prefixes and the plus minus designations that indicate the optical rotation. So the physical property of stereoisomer or racemic mixture. Racemic mixture means that when an equal amount of two enantiomers exist, which means 15R and 15S, we say that racemic mixture or racemate. Especially SN1 reaction is known by the formation of racemic mixture because of the nucleophile can attach either in both direction, either backside attack or front side attack. Due to that reason, they produce what racemic mixtures. So this racemic mixture is difficult to separate actually. So racemic mixture is optically inactive because two enantiomer rotate plane polarized light an equal extent but in opposite direction. Therefore, they cancel each other. The no rotation is observed actually. So specific rotation is standardized physical constant for the amount that the chiral compound rotate plane polarized light. Specific rotation is denoted by the symbol alpha and defined using a specific sample tube length L in decimeter, always concentration C in gram per ml, and the temperature at 25 degrees Celsius, as well as wavelength is at 589. This one is wavelength of sodium D line. So specific rotation is designated like this, equivalent to its observed rotation in degree over L times C, where L is the length of sample tube in decimeter and C is the concentration in gram per ml. Physical properties and of stereoisomers. So enantiomeric excess or optical purity is the measurement of how much one enantiomer is present in excess of the racemic mixture. It is denoted as EE. So EE is equal to percentage of one enantiomer minus percentage of the other enantiomer. Consider the following example. If the mixture contains 75% of one enantiomer and the 25% of the other, the amount of excess is what? 75 minus 25, that is 15. Thus, there is 15% of excess one enantiomer over the racemic mixture. That it means. So the enantiomeric excess can also be calculated if the specific rotation alpha of the mixture and the specific rotation of pure enantiomer are known. Therefore, enantiomeric excess is equal to observed mixture times over pure enantiomer times 100. Always can be it can be expressed in percent. So since enantiomer have identical physical properties, they cannot be separated by common physical technique like distillation. The stereomer and the constitutional isomer have different physical property and therefore can be separated by common physical properties. Therefore, nowadays in natural product drug discovery or in synthetic drug discovery, the headache for scientists is what the existence of racemic mixture, because this racemic mixture or enantiomer can be what have the same physical and the chemical property like melting point, solubility, density, refractive index. Therefore, it is difficult to what separate this enantiomer. Calculate the specific rotation by simply using the formula by taking what given parameters. So what is the enantiomeric excess of the following mixture, which means 95% of A and 5% of B. Therefore, A minus B, that means that is 90%. Given the enantiomeric value, what percent of each isomer, that is almost 60% excess A and the 40% racemic mixture. So 20% of A and the 20% of B excess are there. So you have to add 60 plus 20, that's 80A, and the leave is 20% for B. That means pure compound has specific rotation of 24 and the solution of this compound is a rotation of 10. So what is enantiomeric excess? Therefore, you have to use the formula. Enantiomeric excess is equal to what? Specific rotation of mixture over specific rotation of what? Pure times 100. Therefore, 10 over 24 times 100. So this one is all about chapter 2. It is interesting chapter. So you have to summarize and you have to identify the concept behind stereoisomers. Therefore, thank you for watching. So share and like, subscribe to get more about CNP courses for your knowledge purpose. Therefore, thank you for watching and giving your attention for the concepts as well.